Okay, so let me go over the calendar here. This is we're prepping for the upcoming multiple choice tests, which I'm going to split into 2 days. So we're going to work through our derivative topics between today and Friday. And I'll show you exactly what topics you're going to be expected to know for Tuesday's test. Tuesday's test will be 8 multiple choice questions. They'll be worth 25 points towards your test grade. I am going to ask you to show me your work, so that's going to count towards your grade as well. So that'll be next Tuesday. It'll be a full class period, even though it's EOC week. Tuesday will not get impacted. So that's Tuesday. I think maybe even Monday we can start looking at, or sorry. Yeah, so between Wednesday and next Monday, we're gonna look at derivative topics and review those. And Wednesday, Thursday, we're gonna look at second semester topics, so integral topics. But I'm gonna move the second portion of the test to next, not next Tuesday, but the Tuesday after. That way, because Friday is not a full class period, and I want to give you a full class period, even though it's meant to be a 30-minute test. I just feel like, landing on an EOC day, it's just, it's a little bit hectic. So I'll move it the following Tuesday. But I don't want to spend any additional days on the multiple choice packet. We should be able to finish the packet by Thursday. And then Friday, I want to begin our FRQ packet. Now, your FRQ packet 5 will be counting towards a quiz grade. So as long as you do your assignments each day, you're earning all the points possible for a quiz grade. And then all same with packet 6, but that will be the second week of May. All right, so this will be worth 25 points. This will be worth 25 points. And then the rest of packet 4, which we're working through, will be worth 50 points. And then if you guys are showing me your daily assignments, then you're earning all the points. Otherwise, if you show me late, it's still 9 out of 10 points. It's still fine. But if you show it to me on time, then I'm able to give you full credit for your homework, which is going directly towards your test grade. Okay, any questions about this week or next? Okay. So in your packet 4, I have the key attached. So the key is attached to the back of your packet. So check and make sure that you see that. I also want to let you know that there's a formula sheet for you to reference. Now, the formula sheet will not be given to you on the test, but I just want to give you a formula sheet for you to look through. And I think this is it's not everything, but it's the most important things, page 23 and 24. So if I'm able to condense everything that we've learned into 2 pages, this will be at page 23 and 24. So it has all the most important formulas, all the most important concepts. So I think it's worth your time to look through and begin to commit these to memory, since we still have close to a month before your AP exam. But to be able to look at this on a regular basis, and as well as to look at this as you work through your multiple choice test, I think it's nice that we have all this time to prepare for the AP exam, and it's good if we can take advantage of this time to really get comfortable with all these things that we see here on page 23. Okay. Okay, so page 1. These are all the major topics. that we covered this year. And let me just kind of run through those topics. So we have limits and continuity and L'Hopital's rule. That's from the first unit. And L'Hopital's rule is not the first unit, but it's still limit related. But L'Hopital's rule requires derivative knowledge, right? We first evaluate the limit. If we get 0 over 0 or infinity over infinity, we have the flexibility to do L'Hopital's rule, which is to take the derivative of the top and the bottom separately, reevaluate, get down to our real number. Product rule, chain rule, quotient rule, implicit differentiation. That's where we have y's mixed into our equation and we want to find the derivative. And so a bunch of dy dx's will begin popping up. Okay. Theorems such as EVT, mean value theorem rules, and even IVT. We've been seeing those pretty regularly on our FRQs. Related rates, this is where time is our independent variable. So every variable gets impacted by time after we find the derivative. So remember with the ladder problems where if we have x squared plus y squared equals z squared, we find the derivative of each variable and we attach d over dt for that variable, right? So x squared becomes 2x dx dt, right? Derivative graph, okay? Being able to read the derivative graph, being able to know what the common properties of the original graph based off of the f prime graph. First derivative test for concavity, these are the sign lines. Second derivative test is where we look at the second derivative value to see whether it's concave up or concave down, and from there determine whether we have a relative max, relative min. PVA, this is similar to first derivative test, your velocity sign line, your acceleration sign line, comparing signs to determine increasing, decreasing speed. Trig, derivatives, natural log derivatives, derivative of inverse at a point, linear approximation, we've been working with that. And so 1 through 11 are first semester topics, and then the rest are second semester topics. So the test next Tuesday will just be covering topics 1 through 11. And then Riemann sums, trapezoid approximation, integration rules like U substitution. Okay, you can cross this out. There's no long division, you can cross that out. But we do have synthetic division, so we can put that instead. We do have synthetic division, arc trig, first theorem, second theorem, average value theorem, solving differential equations. We saw that on our quiz yesterday, slow fields, and then area volume, disk method, washer method, cross section. Those are second semester topics. Okay, so our assignment today is page 1 through 4. So we'll work through as much as we can from page 1 through 4. Whatever we don't finish will be your homework, which I will check tomorrow. So tomorrow, I'll be checking pages 1 through. Okay, so let's look at number 1 here. So we're all the way back to limits here. The graph of the function f is shown. At which value is our graph continuous but not differentiable? So continuous means what? What does continuous mean? Yeah, there's no gaps, right? That it's no holes, no asymptotes. So no breaks. What does differentiable mean? Or what does not differentiable mean? Well, what does differentiable mean? Or what does that look like? So what? Yeah, so differentiable means that the derivative is possible at every point. Or the derivative exists at every point. And what that means is derivative exists means that there are no, exactly right, no sharp turns. But here it says not differentiable. So that means we are looking for something that is either a sharp turn or a vertical slope or vertical tangent line. So where do you see a place where there's no break, but there's a sharp turn? 0.8. Yeah, 0.8. So a related question is, where's the graph where the limit exists but not continuous? So that's a related question that I want to ask, where not continuous but limit exists. And you find a point where it's not continuous but limit exists. D. Okay, so the issue with D is that if I pick points on either side of D, are the arrows headed towards D, headed towards the same Y value? They're not, right? So this would be not continuous and limit does not exist, right? For limit to exist, we want the arrows to head towards the same destination, even if that destination doesn't exist. B, yeah, so here, if I choose points on either side of B, the arrows are headed towards B. That's consistent movement, so the limit does exist, but obviously not continuous because at B there's a hole, and so that point doesn't exist, but the limit does exist. Okay, number 2. The function is to find which of the following statements is true. Is it continuous? Is there a removable discontinuity? Is there a jump discontinuity? So anytime I see the word continuous or asking about continuous, I always like to work through my continuity conditions. So continuity conditions, there's 3 of them. The first is, does a point exist? Does the limit exist? And then the third is, does my first 2 conditions equal each other? All right. Okay, so the point in question is they're always going to identify that for you. So in this case, the point in question is 2, because we don't know, between these 2 graphs, is that hole, if there's a hole, is that hole getting covered up to allow for continuity? So the first thing is, does the point exist? So we want to find f of 2. What's f of 2 equal to? 7, right? So this is just a point. The graph is within the first expression. So the first expression says that the function is defined everywhere except 2. So that means to the left of 2, to the right of 2, it's all self-contained within this graph. This 7 is not really a connected graph. It's just a singular point because it's only defined at x equals 2. Okay, so the point exists. To find the limit, though, we have to involve the graph that has connections to it, right? So to find the limit, what are we going to look at? The top one, right? The top one is, this is, when you say doesn't equal to 2, that means everything to the left of 2 and everything to the right of 2 is contained within this expression. So the limit is going to be looking at that. There's no need for one-sided limits because it's not a split graph. It's not to the right, it's one graph, to the left of 2 is a different graph. It's the same graph on either side of 2. So there's no need to do a one-sided limit. I would say you want to do one-sided limit if your piecewise has a less than or greater than. If it's less than or greater than, then that means you have 2 different functions on either side, and you want to see, you don't know if they're going to be in agreement, so you got to do a one-sided limit. But in this case, we can just do a limit as x approaches 2. Okay, first things first, what's our first thing we do with evaluating limit? Plug it in, right? So if I plug 2 in, what do we get? 0/0. Now that gives us the flexibility to apply what? Yeah, L'Hopital's rule. We can also do factoring and reduce, but I think we're probably feeling that L'Hopital's is going to go a little faster. So what's the derivative of the top? Bottom's derivative is reevaluate. What do we get? 5. So the limit is at 5. The point is at 7. Is the graph, well, first off, the limit exists, right? The point exists, limit exists, but are they existing at the same place? No. So f of 2 does not equal to a limit as x approaches 2 of f of x. So what does that tell us? That means there's a what?
This one.
Okay, what type of discontinuity? Yeah, removable, because there's a, is that an asymptote or is it a hole? It's a hole, right? Because this is telling us a visual description of what this graph could look like. That means at 2, 2, 5, there's a hole there because the graph is headed towards both values from both sides of 2 heading towards 5, but the point is living at a different value, 2, 7. So the limit exists because both sides of the hole is headed towards that hole. But obviously there's a break, a hole in the graph. So we call this a removable discontinuity. B. Now, number 3, it says, now if you look at the number 3 here, the function is natural log of x between 0 and 2, but then it's x squared natural log of x from 2 to 4. So if I want to find the limit as x approaches 2, now I need to do what? Can I rely on one limit statement? We need 2, right? We need to look at how the graph is moving for natural log of x and how the graph is moving on for x squared natural log of 2, because we want to see, you know, on either side of 2 and 4, are they going to connect or are they going to disconnect, right? If they connect, then great, the limit exists. But if they disconnect, then the limit does not exist. So we'll do one-sided limit. We'll do the limit as x approaches 2 from the left side of 2. So that means between 0 and 2, that means on to the left of 2, we're looking at natural log of x. And we'll handle that in a second. And then we'll also need to find the limit as x approaches 2 from the other side of 2 for x squared natural log of x. Okay, so if I evaluate this limit here, what do we get? Oh, sorry, natural log of x, natural log of 2. Okay, so how do we evaluate this? What do we do? Plug in what? Just 2, right? No decimals. That minus just indicates we're coming from the left side, but we're always going to look at the whole number first, the integer first. And only if we realize there's a vertical asymptote or there's something weird, then we can worry about decimals. But the decimal is not going to play a role unless in very specific situations. Okay, so this gives us natural log of 2. So that means on the left side, the graph is headed towards a y-value natural log of 2. So we want to see if there's an agreement on this side. If I plug in 2 here, what do we get? So are these 2 arrows headed towards the same destination? No. So therefore, the limit doesn't exist. Okay, number 4, we see a limit, evaluating a limit algebraically. It's a messy expression. So what's the first thing that we should do. Yeah, plug in the pi, right? Let's see what happens, right? If it's a real number, then there's nothing more to do. Right, because we don't have the graph in front of us. We don't know what's going on. So when we see a limit problem, algebraically, it's information gathering, right? Let's see what's going on. Is there a hole there? Is there a point there? Is there a asymptote there? Okay, so pi gets inserted for all the x's. Okay, what do we get here? What's cosine of pi? -1. -1 plus what's sine of 2 pi? 0. -1 plus 0 plus 1. What does that give us? 0. Denominator, we also get 0. Okay, so that allows us to apply what? L'Hopital's, right? L'Hopital's rule. Okay, so derivative. Right. So we take the derivative of each term. Cosine of x becomes negative sine. Sine of 2x becomes cosine 2x. Anything else? Times 2. Yeah, so a little bit of chain rule there. And then the plus 1 goes to a 0. Okay. X squared becomes 2x. What does pi squared become? 0 squared. Yeah, it's not 2 pi, right? Pi is a number, so we don't treat pi like a variable. It's just going to go to 0. Okay, so we have our derivative version. We can now do what? Again, right? Because our whole goal is we're hoping that we can get a real number out of this. If we get a 0 or 0, that's indicating that there is an answer waiting for us. Right now, it's just kind of getting blocked by that hole. So we've found the derivative. We found a different version of our expression, reevaluated it. So let's see what we get. Okay, so pi in for x. Okay, sine of pi is this way. 0. Okay. Cosine of 2 pi is 1. Yeah. Times 2 is 2. So 2 over 2 pi is 1 over pi. Yeah. So the limit does exist. 1 over pi, and this is a good problem for us to see how L'Hopital's rule can look like. And then a side note is if this were free response question, then with L'Hopital's rule, graders are a little bit picky about notations they use. So just try to use arrows as much as possible, unless you know for sure that both sides of the equal sign is the same. I like to use arrows so that you're not, getting points taken off for something like an equal sign. Okay, page 2. All right, what's different about number 5? Infinity, right? So with infinity, we got a different set of rules, right? With infinity, we don't plug infinity in. What do we do? Compare degrees, right? Compare degrees. So the idea is if degrees are the same, we take the ratio of the coefficients. If the degree is higher than the denominator, it's going to be 0. If the degree is higher in the numerator, then it's either infinity or negative infinity. So what do you notice here? What do you notice about the degrees between numerator and denominator? It looks like it's higher, but they're the same because why is that 4 the same thing as the 2? It's a square root, right? So let's not worry about the 1. Let's just clean this up here. If I take the square root of 9x to the 4th, what does that become? 3x squared, right? So this is, so I know that there's a 1 there, but we know the 1 is not going to impact anything because it's too low to impact. So what's the, so we notice, are the degrees the same? Now they're the same, right? Well, now it's easier to see that they're the same. So if the degrees are the same, the limit is just going to be what? And what does that become? Just 3, right? Just the ratio of the coefficients, right? We know that the x squared is going to be the one guiding the limit, and we should look at the number in front of those variables. 3 in front of x squared, and the bottom there's a 1x squared there, so 3 over 1. My limit is just simply 3. It's basically the way that we find horizontal asymptotes. All right, if we were to look at this, this graph is going to flatten out at a y value of 3. It's going to keep holding that, getting closer and closer towards that y value. Okay, number 6, limit as x approaches a. I know this feels a little bit strange. I know that whenever we see a constant that is represented as a letter, it kind of throws us off a little bit, but just pretend like a is a number. Imagine this is like limit as x approaches 3, x minus 3 over x cubed minus a cubed. So what's the first thing we do?
Plug in a.
Yeah. So replace x with what? With a, right? So I get a minus a over a cubed minus a cubed. What does that give us? Yeah, 0 over 0, which allows us to do L'Hopital's rule. And remember, a is just a number, right? Okay, so let's find the derivative. X's derivative is 1. A's derivative is 0. Yeah, remember a is just like a 3, right? A 3 will go to 0, same as an a. A is a constant. A is also going to go to 0. So x becomes 1, a goes to 0. Denominator, x cubed becomes a cubed goes to 0. And so now we have our different version of our expression. We want to find the limit. So next step, yeah, plug in, right? So what's our limit going to be? Okay, number 7, we want to find the derivative. This is a product quotient, chain rule, and power rule. So here, f of x equals x cubed over cube root of x. We could go through quotient rule, but why don't we can just merge it, right? We have a variable above, variable below. We can just put it all together and just do power rule. So let's see if we can just rely on power rule, especially now, if there's x cubed minus 1, or if there's multiple terms below, we have to go through quotient rule. But here, there's only one variable. We can just easily move things around, merge it together, and just do power rule. So let's see if we can merge it together. Let's get that radical out of the way here. What's cube root of x? Same thing as what? So I can bring that x up to the top, right? So if I move that x to 1/3 up to the top, what does that become? Yeah. If I want to do x cubed times x to the negative 1/3, how can I merge it into the same variable? Good, add. You only multiply if the variables are if the exponents are directly next to each other. If those x to the cubed to the negative 1/3, then you can multiply. But here, we're going to be adding those exponents. So 3 minus 1/3 is what? Yeah. Common denominator, 9/3 minus 1/3 is 8/3. So now this is the same thing as this. And now if you just do power rule will get me to the derivative. So let's find f prime. 8/3 x to the 5/3. So we just have to find an appropriate variation from our answer choice. So if I rewrite this 8/3 times the cube root of x to the 5th, there's 5 x's inside. I need 3 to allow for 1 to come out. So this is the same thing as cube root of x cubed times x squared. For every group of 3, I can pull 1 out. So 8/3 x. And then the remaining 2 is not going to come out. So that's going to be left inside. So I'm just matching it to the option that we have available here.
You put that multiplication sign in the middle, or just put a 3x next to this.
I just show that. I just want to show that that cube is this cube root is not part of the x, so I just separated it. But yeah, you don't need that. You can also use parentheses. I just didn't want that cube root to be misinterpreted as part of the x. Okay, number 8. Let f and g be differentiable functions, so no sharp turn, smooth curve. G of x is greater than 0. F of 0 equals 1. It says h is equal to f of x times g of x. H prime equals f g prime. So there's a lot of things going on here, but we know that they're referencing the derivative, right? Let's just focus on this part, right? If I asked you to find the derivative at that stage, what would you use? Product. Okay, so let's build product rule and see how our version looks different than their version, and then see why is it different between our version and their version, and then decide what must be true if certain things are different. So how would you build the derivative using a product rule at this stage? Yeah, f prime of x. Yep, then plus f times g prime. Now, does our h prime look the same as their h prime? Okay, but are there parts that look the same? Okay, so these are the same, but what are they leaving out? F prime g. Why would they leave this out? What's happening to this that's allowing them to leave it out? Okay, that means one of these is going to be what? 0, right? One of these is 0. We know that this is zeroing out. That's why they're not including it. But which one? Right. F prime of x. That's right. Good. Yeah, good point. G of x is greater than 0. So we know g is a number. That's not going to be 0. F prime must be the culprit, right? So f prime must be equal to 0. So if f prime is equal to 0, what does that tell us about f? F must be a what? Constant. Constant. Okay. So you can kind of tell that this is, in terms of algebraic steps, it's very little, but it's more like conceptual, right? Just kind of, doing a little bit of detective work to figuring out, why is things the way they are. So f is a constant. So that means f of x is just going to be equal to what? What's the constant? 1, right? If f of 0 is 1, then f of x is also 1, because it's just a constant. It doesn't matter what number you plug in. So f of x is 1. Not difficult algebraically, but it is difficult in terms of making those conclusions from one step to the next and using product rule to go through your detective steps. Okay, let's look at number 9. Let f be a differentiable function. F of 2 equals 3, f prime of 2 equals -5. And let g be defined by g of x equals f of x, f of x. Which of the following is an equation of the line tangent? So what information do we need if we want to do tangent line equation? Okay, we want to find point and we want to find slope. Okay. So let's, it'll be easy if we're just creating tangent line for f, but we're asking to do a tangent line for g. So let's find the point first. Let's find g of 2. How can I find g of 2? Do we have a formula for g of x?
X.
So replace x with 2. So g of 2 is 2 times f of 2. Do we know what f of 2 is?
3.
3. So 2 times 3 is 6. Okay, so we have an order pair. Okay. Now, if I want to find g prime or g prime of 2, I first have to find g prime of x. To find g prime of x, we got to first go through what? Product rule. Yeah. So let's build product rule here. Product rule is f prime g plus f g prime. So let me label that here. F prime g plus f g prime. Okay. So this is my first term is my f, second term is my g. Okay, what's f prime? 1 times f of x plus x times f prime. Okay, so I have my slope formula. Replace every x with, trying to find the slope at what? 2. Yeah, so g prime of 2, right? And do we have enough information to get this down to a number? Okay, f of 2 is 3. F prime of 2 is 5. So my slope is -7, right? So I have everything that I need. I have my order pair. I have my slope. Now point slope form, right? Page 3, let me look at 11 with you. Okay, number 11. The function above shows the graph of the function g. So here's g right here. And the line tangent to the graph of g at x equals -1. So tangent. Let h be the function given by h equals e to the x times g of x. What is the value of h prime of -1? Okay, so before I can find h prime of -1, I first have to find h prime of x. To get to h prime of x, I have to go through what? Okay, to find the derivative, what's involved here? We'll use product rule. Okay, so let's build the derivative using product rule. So f prime, what's e to the x's derivative? That's e to the x. Okay, so f prime times g plus f, and then g prime is just going to be g prime. Replace every x with -1. So e to -1, those are resolved. I mean, we can bring the e down to the denominator, but we're done with them. The only thing left is we have to figure out what's the numeric value for g of -1 and g prime of -1. G of -1 is easy, right? What's g of -1? 3. Okay, good. Now, what's g prime of -1 asking for? The slope of the g graph at -1. I don't have a formula for g of x. So how can I find the slope of the g graph at -1 if I don't have the formula for g of x? Yeah, I have this line, right? So what do I know about the tangent line and the slope and the slope of the graph at that point? They're the same. So if I can find the slope of this line, it's going to also be the slope of the curve at that point. Okay, so how do I find the slope of this line? Yep, change in y over change in x, right? So -3 minus 3, or you can just count. If you want to count down and over. Yeah, so -6 over -1. Sorry, -6 over 1, that's -6. And answer choice D. Once you bring the e down to the denominator. Okay, so homework pages 1 through 4. Come get your phones. Thank you. Thanks. Are you talking about it's not different or something? You wanted something. Oh, first thing. Yeah, you're cool. Have a great day, guys. Hi, it's yours. It's kind of, how many do you have? Take one and